Okay, so let's look at lag compensators. So we learned that lead compensator contributes an angle which reshapes basically the root locus, and by that it can move the location of the dominant poles to the desired location. And so it changes the transient response characteristics, such as damping ratio or natural frequency, or in other words, it can change the maximum overshoot or rise time or settling time and so on. But the fact is, a lead compensator cannot really affect much the steady state error of the system. So when we have if you remember in class, I mentioned a good controller is the one that shows minimal overshoot, is fast, which means small settling time or rise time, and also the one that shows minimal to zero steady state error, right? So lead compensator can take care of the speed of the response and the overshoot. But again, it does not have much of effect on the steady state error. So we learned that steady state error for different types of inputs, we define that it depends on the type of the system, and we define some terminology, some basically parameters like Kp, Kv, and Ka in response to step, ramp, and acceleration inputs. And we learn that the bigger the Kp, Kv, or Ka is, means the steady state error is smaller. So the goal of a lag compensator is to boost up or increase those numbers, Kv, Ka, or Kp, especially in this examples, we're going to see Kv mostly, but not specifically, it can be any of them, but again, in this example, mostly Kv. And so by increasing Kv, it's going to bring down the steady state error, yet at the same time, while improving the steady state error, the lag compensator is not going to reshape the root locus the way a lead compensator did. It's going to have very, very minimal effect of the lead on the lead and the root locus, because if it does change the root locus, then it's gonna ruin the transient response. So we want lag behavior to be quite independent of a lead behavior. We want each one of them to do a separate job and not affect the improvement that the other one made. Okay, so the goal of the lag again is to boost up the gain of the system without changing, as here says, the transient response of the system or changing the root locus much. Now, how can we achieve this? So a lag compensator transfer function is very similar to lead. It has a gain, a zero, and a pole. The only difference is here, the pole is closer to the imaginary axis than zero. Okay, so the location of pole and zero is reversed, and here beta acts similar to alpha in the lead, with the difference that beta here is bigger than 1 instead of less than 1 that alpha was. The other thing is, we know when we add a zero and a pole, it does really change the root locus, right? We just learned that adding a pole shifted to the right, adding a zero shifted to the left. So how can we add a pole and zero without really shifting and changing the root locus too much? And when I say that, what do I mean? Let me show you in this picture. So here, we're going to go through this example right now, but this is the original system, which has relatively good transient response. The only thing is we want to boost up its Kv from 0.5 to 5. So we want to make the steady state error 10 times smaller and without changing the transient response. And you're going to see when we design a lag compensator and add it to the system, if you can watch here, The two curves here are the root locus of the original system and the one with lag compensator. And you can see they are almost on the top of each other, okay? So when you look at the difference between them, if you zoom out, you're not going to see much. The only difference is if you zoom around the origin is when you're going to see the differences, okay? So in general, we don't want to reshape and change the root locus significantly. So unless it's around the origin. Now you might say, why origin? And what's the meaning of that to the pole and zero of the lag compensator? So first of all, why the lag compensator will change the root locus only around origin? So in order for that to happen, we choose the pole and zero both, as it says here, first of all, close to each other. The other, we choose them close to the origin. So we are not going to choose like the pole or zero, like at the previous example, the pole was at negative 4.6 or something. No. Here you're going to see in the example we are going to solve is we choose pole and zero of the lag, very small numbers, very close to the origin. So they only affect the origin. And the other thing is, why origin? It comes from the definition of the KV or KP or KA, those error constants. For example, if you look at the response to ramp and KV, so KV is limit of what? S times the open loop transfer function. So if we assume original system was G and the compensated one is what? GC times G, because GC is in series with G. So what is it that is forming the behavior of the system in response to in a steady state? That's KV, right? We want bigger KV to have a smaller steady state error. And KV is determined by the limit of this function GC as S goes to where? Yes, 0. And 0 means origin. Okay? So your location of the in the imaginary, in the complex plane is determined, the steady state error, the steady state behavior of a system is only determined by how the system would appear around what? Around 0. So it does not care, the steady state response does not care how you behave, how the root locus looks like where it's not close to the origin. So these areas here, they are not really super important to the steady state. They are important for what? Transient response. But at S goes to 0, this area only, that the shape of root locus over there is going to determine how much the steady state error is. Okay? So again, that comes from this limit of S goes to 0. Now, how do we design a lag compensator? So again, some important things we have to keep in mind. First, we choose the pole and zero very close to the origin and close to each other also. The angle contribution, or in other words, the angle contribution of this lag should not be more than 5 degrees. If it is, then it means it's going to reshape the root locus and the transient response, which we don't want. So that's one of the things, choose them close to each other. The other thing is, so you see, we are just going to choose them, okay? And the important thing is this gain KC also, we typically choose it very close to 1. At the end of the day, you see that it's going to be close to 1 because if we look at the constant KV, the one that we are going to change, it is the limit of SGS times GS goes to 0. Now, what is the limit of GC, the lag, as S goes to 0? So if we go and look at here, what is that limit? So when S goes to 0, clearly you have Kc times 1 over T divided by 1 over beta T. So it's going to be Kc times beta, and that's what you see here, okay? So the new KV is going to be the original KV times Kc times beta. Now, if, for example, I want the new KV to be 10 times bigger than the original one, then I have two parameters that I can choose to make it 10 times bigger. But what I typically do in a lag compensator, I choose beta to boost up KV or change KV. So if I want this, again, new one to be 10 times bigger than the other one, I choose beta to be around 10. And then Kc, you're going to see it's going to be around 1, which is quite obvious from here, but also the effect of that Kc not being too bigger is it reshapes the origin only through its pole and zero, not through that gain. Okay, so ultimately we're going to find Kc by the magnitude condition, that the magnitude of the compensated system at the desired location should be equal to 1 at the dominant pole. So we're going to use that. So the overall procedure is this. First, we draw the root locus for the uncompensated original system. Then, based on the transient response, we determine the location of the dominant closed loop poles. And then we basically, based on the difference between new KV and original KV, or Ka and original Ka, we choose beta such that it makes this change happen. And then based on beta, which is the ratio between the location of what? Pole and zero, right? If you go back here, the zero is at 1 over t, the pole is at 1 over beta t. So if beta is 10, 10 is the ratio between what? Location of zero and location of the pole. For example, if zero is at 0.5, then pole is 10 times closer to the origin, which is 0.05. Okay, so that's beta is the ratio between the location of zero and pole. So using that, we determine zero and pole. We choose one of them, basically means choosing t arbitrarily, and then the other one will be determined since we know beta. And then finally, we tune Kc such that the magnitude condition is satisfied. So let's look at this example together. So here we have a physical system with this transfer function third order, type 1, and the dominant closed loop poles for this original system are at these locations, which of course we can easily find out. But that also would give us that the KV velocity error constant is 0.53. Now we want KV to be much bigger, like 5, so that the steady state error goes down in response to a ramp input. So we want to do that, but we do not want to move these dominant poles much from where they currently are. We are satisfied with the zeta and with the omega n overshoot and the stuff that they give us. The only thing we do not like is this small kV, because if you remember, steady state error was 1 over kV, so 1 over 0.5 is 2. So you're going to have 2 units error in response to a ramp function. But if you make it 5, now the steady state error is 1 over 5 is 0.2. So steady state error is going to be much smaller, but at the same time, again, we are not going to change this original root locus significantly. We're going to get something very close to it, but just jumping up this KV. Now, how do we do it? So this is what we do. First, it's 1.06. So if I go back here, the closed loop transfer function for the original system is, of course, g over 1 plus g times h, which is 1. So it is, if you simplify with this g, right? So we have this g. If you plug that in and simplify, you are going to get 1.06 divided by s times dou. So it's going to be s cubed plus 3s squared plus, write that nicely, 2s plus 1.06. Okay, so this is the original system. Now, if you look at the characteristic polynomial, and we find the roots to this guy. So let's do that. So the roots to 1, 3, 2, and 1.06 is at negative 2.34, negative 2.34. So S1 is negative 2.34, and S2 and 3, which are complex conjugates, are at negative 33 and 59. Negative 33 and 59. So clearly this is not a second order system. We have 3 poles. One of them is a real number, quite bigger than in magnitude the real part of the others. So if you see here, these 2 will lead to what? To an underdamped behavior, oscillation with damping, but their damping is due to this term, exponential negative 0.33t. This one is just a pure decaying exponential, but the exponential power is 2 times 3.4. So it's like 8 times bigger than that. So this one would decay quite fast and go away, but these guys would stay. So we call these 2 to be what? Our dominant pole. And from these 2, we can find our approximate zeta and omega n and everything, okay? So if somebody says, what is the damping ratio for this system? Again, we do not have a second order system, so we look at the linear term coefficient and say, hey, the linear term coefficient is 2 zeta omega n, and then this constant is omega n squared. No, it's not. But if we approximate this by a second order system with these 2 dominant poles only, then we know the poles are in general what? Sigma plus omega d times I. Now your sigma, which is zeta omega n, is 0.33, and your omega d, which was omega n square root 1 minus zeta squared, is 0.59. And so from here, I could find both omega n and zeta, and then from there, I can also find what? I can also find any other thing. So for example, here you can see that omega n is clearly square root of sigma squared plus omega d squared, which if I do it, so 0.33 squared plus 0.59 squared is 0.67. Let's make it 0.68. Let's just use 2 digits for now. 0.68. And then zeta, of course, is going to be sigma over omega n, which is 0.33 divided by this number. So 0.49. Okay. So you see zeta is around 0.5. Omega n is a little small, but the designer of the system is happy. Okay. So again, from here you can find maximum overshoot. And then you can also find from here and here, you can find rise time, settling time, and so on and so forth, right? So you can find all other things, T rise, T peak, settling time, and so on and so forth. So we can completely define from these dominant poles the transient response of the system, which we are happy with. But now it says it will put the KV at some number, right? So it says the KV of this system is 0.53. Is that the case? Let's just check it. By the way, you see these poles are exactly what I found here for you. So now, what is KV? If you remember, KV was what? So KV was the limit of S times open loop transfer function, which for original system is just GS as S goes to 0. Is that correct or no? What would you say? Clearly you see the definition. And GS in our case is this guy here, not this one, the one in example, which is this one, 1.06, right? So it is going to be limit of s times 1.06 times s plus 1, s plus 2 as s goes to 0. This one would cancel, and you are going to get 1.06. Plug in 0 here and here. These two would disappear. It's 2, so you're going to get 0.53 seconds inverse. So that is the kV of the original system, which we don't like, and we want to make it 10 times bigger. So how do we do that? So this is the way that we design it. First, the new kV, if we call it kV hat, is 5, right? So the new kV is 5, which is Kc, the gain of the compensator, times beta times old kV. And the old kV is 0.53. So you see that this number should be 5 divided by 0.53, which is around 10. So what we do is, since Kc should be around 1, okay, this Kc should be almost around 1, and this ratio is around 10, what I would choose, I choose beta to be exactly 10. I can choose it to be exactly the ratio and try to get Kc close exactly 1, but typically we go with an integer beta to make a location of calculating the location of 0 and pole easier. So we choose beta to be 10. And so 10 means what again? 10 means that the pole is 10 times closer to the origin than the 0. So here it's time to choose 0 and pole of this compensator. So the compensator GC is Kc times s plus 1 over t divided by s plus 1 over beta times t, and beta in this case is 10. Now, how do we choose them? Again, the other requirement is both of these, pole and 0, should be very close to origin. Both of them. Although one is 10 times closer, but if you choose the bigger one very small, the other one would be even smaller. So what I choose is a small number for the 0, which is a little further away. And what I choose for this whole number is, this is arbitrary. You can choose any number you want, but I make sure this is small. And when I say small, what do I really mean by small? So that is determined kind of by the root locus of the system. If you look at the root locus of the system, the branching point here is somewhere between 0 to 1. It's actually -1. Let's see. 0, 1, 2. It should be -1 actually. But the breakaway point is somewhere between -0.5 and 0. And so what we want is both of those poles and zeros are actually quite away from this breakaway point. So if our breakaway point is here at 2 or 3, maybe we have a little more room to choose a little bigger 0 pole, although that's not a good idea. But when this system has this breakaway point very close to origin, we want to push them as close as possible. Of course, not like super crazy small, like 10 to the -8 or so. So if you look at your textbook suggested using this as 0.05. And so this one will be 0.005. Okay, so in other words, T is what? T is 20, right? Or 1 over that, right? So it's going to be, yeah, that should be 20, 1 over 20. So it says choose T to be 20, beta to be 10. So that's the location of pole and 0. And now that I have both of these guys, then what I can do is to find the gain Kc, right? Now this problem, as you can see again, does not like you to change the location of this dominant pole. Say these are good enough. Just make sure that the overall gain of the open loop, new open loop transfer function at this location is exactly 1. So the only thing we need to do is the magnitude of the new open loop transfer function, GC times G, at one of these guys, which was negative 0.33 plus 0.59i, that should be exactly equal to 1, right? And so GC in our case is KC times S plus 0.05 divided by S plus 0.005, and then multiplied by 1.06 times S plus 1 times S plus 2. The magnitude of this, that's S equal, again, negative 0.33 plus 0.59i or negative 0.59i should be exactly equal to 1. So we plug in this S here, we're going to get a bunch of complex numbers, we find their magnitude, and then divide 1 by the product of all of those. You're going to see Kc will be 0.96 or 97 actually. Okay, so now that I have Kc and I have 0 and pole, I'll completely know my compensator. And so what I would do is I would plot again the root locus of the original and the new one, and I'll show you that there is not too much difference in the root locus. The only difference is the kV of the new system is much bigger than the original one, and so the steady state error is smaller. Okay, so the original system, if I come back here, is I say draw for me R locus of, and also I guess the problem is asking about their responses, right? Doesn't it say so? No. Okay, so R locus of 1.06 and S times S plus 1 times S plus 2, which is this guy. So this is the original system, which you can see in the PowerPoint 2. Now what I want to do is the R locus of this new one. So that one multiplied by this, right? 0.97 and then the pole and the 0. So I multiply that gain by 0.97 and then again multiplied by, that's times S, and then that's times 0.05. So this one and this one, these are the coefficients of the numerator, and then the denominator is that term times one and 0.005. Okay, now this is going to overwrite the previous one. So let me use a figure and redraw the previous one. So this is the original one, this is the new one. Clearly can see, you can barely see any differences, or almost exactly the same. The only difference is exactly again here where you added a 0 and a pole. Okay, so here the only thing that you have added is this loop that here you don't have. right? So that's the only difference. So here, by adding one pole here and 1 0 here and the original pole at 0, now you're adding a small loop, and this one is all the difference, which if you zoom out you cannot see any differences much, but that is enough to change the response of the system around origin, which means bringing the steady state error down. So hopefully you learn how to design a lag compensator.